Hello, and welcome back to Electrochemical Engineering. Today I'm going to talk about battery cell and pack design, and this material is largely taken from Fuller and Harb's Electrochemical Engineering book. This photo I show is of a battery pack, a battery module, one of 16 battery modules that make up the battery pack in a Tesla Model S. And through this lecture, you'll understand to some degree how this type of system is engineered. So let's think about battery design. A battery, of course, refers to an assembly of individual cells. The individual battery cell is what we've primarily discussed up to this point. Let's consider, for example, a lithium-ion battery for an electric vehicle. Imagine this battery requires 2 hours of discharge time, a total energy of 24 kilowatt hours. This is equivalent to joules. Kilowatt hours is a unit of energy, like joules is a unit of energy. It needs a battery output voltage of 360 volts and has a single cell voltage of about 3.75 volts, typical for a high energy density lithium-ion battery cell. Now, we could calculate the number of cells you need in series, we're going to call that M, in order to get that required voltage. So we take the voltage of the battery and just divide by the voltage of an individual cell, and you see we need 96 cells in series. Now this is called a string. An individual string of cells in series whose voltages add. So we have M times V cell equals the voltage of the battery. We can put these strings in parallel to increase both the battery capacity and its power, or decrease the capacity of an individual cell if you wanted to use differently sized batteries. So more generally, we're going to define the number M as the number of cells connected in series in a string. You'll see the abbreviation S sometimes in literature. And N, the number of strings connected in parallel. This could be P in the literature at times. So if I go back to this diagram, you can see M is this direction across this array, and N is the number of strings up and down. If we used two parallel strings, the total number of cells would be M times N, which is 192, since we decided we were going to have 96 batteries in each string. Now, we could use this information to calculate the needed energy in each cell. The energy of a cell is going to be the capacity of the cell times the average voltage of the cell. Cell capacity, of course, is in amp hours. It's a different unit for capacity. Coulombs would be the SI unit. And the average cell voltage during the discharge. The energy of the battery is just the total number of batteries times the energy in each individual cell. We can rearrange and calculate the capacity of each cell. That's equal to the energy of the cell divided by the voltage of the cell, which is just equal to the energy of the battery divided by the number of cells in the battery. This part is equal to E cell divided by V cell. We can plug numbers in. So we said that we wanted a 2400 kilowatt hour battery. We had 192 cells total and 3.75 volts, and that gives us 33 amp hours. So that's the individual capacity of a cell for this battery pack. The general nomenclature for battery layout is MSNP, where you have M cells connected in series. That's what the S stands for. So that's the number that are in an individual string hooked up in series. That tells you what the voltage is. M times the individual cell voltage tells you the pack voltage. NP is the number of those strings that are then aligned in parallel. So if R total is the total resistance of the battery, that is, if you imagine this entire assembly of cells, looking at it like an resistive circuit element, so the resistance to charge or discharge under a given set of conditions. We can define that in terms of the internal resistance of each individual cell. So of course, if you have more cells in series, M is the cells in series, the resistance will increase linearly with the number of cells, but it will decrease as 1 over the number of strings connected in parallel. And you can see this explicitly in the form of this expression. Specifically, series connections M increase battery resistance and increase the battery voltage. Parallel connections N decrease battery resistance and increase the capacity and the current or the power. So the total voltage of the battery is just M times V cell, and the current of the battery is just N times I cell, where I cell is the current through an individual cell. And if I go back to this schematic, you can see that I cell is constant going through a string of batteries that are in series. This is, of course, a consequence of conservation of current. If a battery is ohmically limited, the total battery voltage is going to be a function of the current flowing through any individual cell. If you could think about a string of a whole bunch of batteries in series, if there are M cells in the string, the battery voltage is just the open circuit voltage for an individual battery minus eta ohmic for that individual battery. So this is going to be V cell under some current condition, I cell, times M, the number of cells that are hooked up in series to make your battery. Power is, of course, current times voltage. So it's the total current going into the battery times the total voltage of the battery. Here we have to take into account both M and N. M is the number of cells in a string. N is the number of strings in the battery. Each individual cell has I cell flowing through it and gives a voltage at that I cell that is given by the open circuit voltage minus eta ohmic, the IR losses. So if I want to know the total power of a battery, I just need to take M times N, which is the total number of cells. You can see this by considering the square array of cells here, times the power through an individual cell, which is what I'm drawing a red square around. However, this doesn't account for the resistance of the connections between the cells. So not only is there the internal resistance of a cell, we're modeling all that kinetics and transport and internal ohmic resistances as a simple internal cell resistance, we have to add in the external cell resistance here, which is simply that of the wires between the cell. So our total is now going to be our external plus the internal resistance from before, which increases as you increase the number of cells in a string and decreases as you increase the number of strings, N. Here we're defining the total external resistance. We're also going to find Rw. Rw is the combined wire and connecting resistance between cells and on each end of the string. And we can go back to this diagram and consider what this is. You can think about having R internal inside each cell, and then Rw in between the cells, etc., down the length of the string. We can write R external here simply as Rw times 1 plus the number of cells in the string, because there's one extra Rw at the end of the string, one more than the number of cells in the string, and divided by N, the number of strings in your cell. This is an approximation because there's other pieces, wires in a battery module or battery pack that this doesn't account for, but it's a reasonable approximation. And then we add to that our internal resistance due to the battery itself. In class, we'll do some examples of different battery layouts, and we'll also talk about battery modules a little bit more through the in-class work. Here's again the photo of the Tesla Model S module. It has, I believe, 144 cells in it, individual 18650 cells. And typically when you use these very large number of cells, you group them together into modules. So you don't have just one M times M array. You have many. For example, we could make a 2S 2P module that had 2 cells in a string and 2 strings. So M equals 2, 1, 2, N equals 2, 1, 2. And we have 2 or more modules, in this case connected in series, though they could also be in parallel or in some other combination to make our entire battery pack. Let's now talk about the scaling of cells. Cells include what's called the ancillary components. This is the casing, the metal casing around the outside that holds everything together. Safety reliefs in case the battery overheats and outgasses it. You don't want to explode, you want to release that safely. Terminals for making electric connections to. How do you reduce the ancillary components of a cell? Well, one way to do that in a battery is to group cells into modules so you have less of these things, or to increase the size of the individual cells. This is what battery makers like Tesla and others have been doing is making the cells bigger and bigger and bigger to get the fraction of the material that makes up the battery to be as much as possible active material as opposed to ancillary material that doesn't store energy but's needed to get the current in and out. Let's talk about a specific example. We'll talk about how we think about writing a set of equations that describe the capacity, the performance of a cell as a function of the size. So let's consider a lithium thionyl chloride battery. This is a primary battery. That means it's non-rechargeable, of course, and it has high energy density because it's going to use lithium metal and thionyl chloride reacting, releasing much free energy to form lithium chlorides, sulfur, and SO2 gas. In this kind of battery, we need room for both the gas evolution, the SO2 upon discharge, and the decreasing electrolyte volume. So let's consider a specific cell geometry shown here in figure 8.3 from Fuller and Harb. Here we have a central lead connected to a positive electrode, which is going to be the thionyl chloride electrode. It's going to accept the solid lithium chloride and sulfur that's formed upon the decomposition of SOCl2. Next to that is a separator. That separator will wrap around the positive electrode so that current can flow, ionic current can flow on 3 of the 4 sides of this central positive electrode. Through the separator, which is of course wetted with electrolyte, to the lithium metal negative electrode. And that's going to be a lithium metal foil that wraps around the positive electrode as well. The whole thing is encased in a cell can that's typically made out of some non-reactive metal, like in this case copper. We can write the total volume of the cell as the volume of the negative electrode plus the volume of the positive electrode plus the volume of the separator plus the volume of the negative current collector, which is essentially the can, plus the volume of the positive current collector, plus any excess volume that's needed to make sure you can have safe operation. And so the question is, how do you design a cell like this that effectively optimizes all these individual volumes for optimal performance? So we can easily calculate for a given capacity here in amp hours. Again, amp hours is just a unit of total charge, just like coulombs. We can calculate the negative electrode lithium volume just using Faraday's law. So the total volume is just going to be the charge we want to store times the molecular weight of lithium divided by the density of lithium divided by Faraday's constant and multiplied by a design factor that is needed to account for the fact that some excess lithium is needed. That is, we don't want to consume all the lithium, even at full discharge, for this particular type of cell. 3600 is included here in this formula just to convert amp hours to coulomb. So you should work out all the units here and convince yourself this is going to be a volume and what that volume would be depending on what you put in for these various parameters. So this is the volume of just one component of the total cell. That is the negative electrode, the lithium that has to wrap around the positive electrode and separator. Now, we can also calculate the volume of the solid products. Remember, this is the overall electrochemical reaction. 4 moles of lithium react with 2 moles of thionyl chloride to give 4 moles of lithium chloride, a mole of sulfur solid, lithium chloride is also a solid, and a mole of SO2 gas. So if we take the amount of lithium chloride and sulfur generated, we can figure that out simply by taking the total charge passed. Again, here it's charge in amp hours, and we're converting from amp hours to coulombs with 3600. And we multiply that simply by the molar mass of lithium chloride divided by the density of lithium chloride times Faraday's constant, plus the molar mass of sulfur divided by 4, because there's 1/4 the sulfur as we have lithium chloride, again divided by Faraday's constant and the density of sulfur. So again, you should go through the math here and make sure you understand how these units work out to provide you with a volume of the solid products. So we can use this now to calculate the total volume of the positive electrode. And that's going to be made out of porous carbon. The carbon is there to act as an electronically conductive porous solid where the electrochemical reaction can take place. You can extract current from the electrode, but the solid products, remember the lithium chloride and the sulfur, can remain trapped and held in that porous carbon. So the volume of the positive electrode then is just the total volume of the solid products you want to store divided by epsilon, which is going to be the porosity of the electrode. Epsilon, remember, epsilon is between 0 and 1. If epsilon is 0.5, it means that about half of the electrode is porous to start, so you only have half the total positive electrode volume to store your solid products. So the overall positive electrode needs to be twice as big as simply the volume of the solid products. You have to multiply all this by, again, our design factor, because you need some excess pores even at full discharge. If you clog all the pores, you're going to have trouble with mass transport at high states of charge. So we can plug in our expression from above to obtain this equation at the bottom. We also have to think about the volumes associated with the separator, the negative and the positive current collector. So the sum of the separator volume, the negative and positive current collector volume, scales linearly with the area of the cell. This is going to be the cross-sectional area here. This is going to be the cross-sectional area here of the cell. And the way Fuller and Harb have done this calculation is they take the thickness of the component, here is the separator, and the thickness of the current collector, here out here, but they take half the thickness of the positive current. And that's because what they're considering to be a cell, a single cell, is sort of 1/2 of this overall wraparound cell. So you just take this thickness, this thickness, this thickness, and half of the interior thickness. And that's just due to the definitions here. We also need to think about the amount of gas we're forming and the excess volume we need for that. And that's just going to be proportional to the amount of capacity we want our cell to hold. And of course, a design factor, which depends on how much pressure our cell can withstand. So we can write now an expression for the total volume of the cell in terms of all these design parameters. Now, how do we use this to think about cell optimization? So let's do a simple example. Imagine you have a cell with capacity Q0 and volume V0. Notice this is not italicized, it's not voltage, it's volume. And you want to double the capacity, but keep the discharge time constant. Okay, so if you double the capacity and keep the discharge time constant, your power will increase essentially by a factor of 2. So option 1 that you could design for would be the smallest increase in volume needed that keeps area and delta of our ancillary, the current collectors, the separator, constant, and increases essentially only the thickness of the electrode. So let's just increase the active components of the cell. But what's the problem with just increasing the active components of the cell? Well, if the area is constant, that means you get twice as much current through any given area element. As the current goes up, the polarizations go up. What are polarizations? There are overpotentials. Eta ohmic, right? Eta kinetic, eta mass transfer. All those overpotentials you've come to know so well. That gives you less free energy, less cell potential, lower efficiency, and you'll reach the cutoff potential sooner for your battery, so you have a lower effective capacity. You reach the cutoff potential sooner because you're giving away more of your free energy for the chemical reaction to drive these polarizations. You can also get non-uniform currents that lead to other problems like precipitation and other things discussed previously in Chapter 5. The total current, of course, is just the total capacity of the cell, capacity in amp hours, current here in amps per meter squared, divided by the time of discharge and the area of the cell. So this right-hand side depicts option 1, which we just talked about. And that's where simply we doubled the size of the 2 active components, right? Just doubled the size of the 2 active components. Now let's consider option 2. In this case, we're going to keep the electrode thickness constant, but we're going to increase the cell area. So in option 2, we've doubled the cell area. That means we've now doubled the amount of ancillary we need to use, but the thickness of the electrodes are the same. So our average current density is constant, and thus option 2 does not have the same issues as option 1. But of course, option 2 uses a lot more current collector and separator, and the electronic resistance of the current collectors is also increased. So let's consider option 3. This is shown in figure 8.5, where we scale the current collector thickness with the cell area. So we scale both together. As the current collector thickness goes up, the resistance of the tab in the current collector goes down. And this is showing in a given simple model how the capacity and the volume scale for option 1, option 2, and option 3. So option 1 will give you the highest capacity for the lowest volume. So if you need a battery that discharges slowly but lasts a long time, option 1 is good. Option 2 is somewhere in the middle. And option 3 has the worst capacity for a given volume, but because we've increased the thickness of the current collector, scaling with cell area, we've maintained the same power as in option 1 as we increase the capacity of the cell. You can model it like this. So this is the resistance of the cell, and this is the resistance in the plane of the current collectors. Here, our current collector, our current collector. This is the tab resistance, our tab. This is a little tab here we are actually going to wire a connection to wire all these cells together. Our tab here. And you can see that the thickness of the current collectors really will affect the magnitude of these resistances, whereas the amount of electrode material will affect the resistance internally. So all these things need to be taken into account when you're designing a battery system. Another thing you can do is stack cells together to increase capacity. One way to do this is put active material on both sides of the current collector. Copper, for example, is a negative electrode in a lithium-ion battery, aluminum for the positive electrode, and tabs are at the bottom and top to collect the positive and negative current. So in this way, you can see that the current collectors, negative current collector here, this is the positive current collector here, positive current collector here. Each current collector is essentially used twice because it can collect current from both sides. And that allows you to reduce the amount of current collector material you need in your cell. But the tabbing does become a little complicated because you do need to connect each one of these tabs in order to make this sort of design work. Note this is different than the bipolar electrodes we talked about in the fuel cell and electrolyzer geometries, because these positive and negative electrodes are made out of different materials. The positive electrode is aluminum, negative electrode is copper, so you can't use the aluminum electrode also as a negative electrode. You have to use it as the positive electrode, because if it's used as a negative electrode, it will get intercalated with lithium, for example. So typically these are tabbed. Each one is tabbed, and they're not done in a bipolar geometry like fuel cells. And that's all I have for you today, and I look forward to talking with you more about this in class.